Alright, silly people, here's the situation. We are going to be using the WKB method to um, estimate, or approximate, I guess, the energy eigenvalues for the simple harmonic oscillator. Um, so, the way to do this, in general, if you're doing the WKB approximation, you're going to find your energy eigenvalues by taking the integral um, bounded by the classical turning points of given energy. It'll be the root 2m times this energy, E, minus your potential energy, V of x. This is assuming one dimension. Integrated over x, and then setting it equal to, I think Sakurai calls it a parity constant, uh, where it is just actually pi h bar n plus 1 half. And that's going to give you your approximate energy eigenvalues. So um, to do this for the harmonic oscillator, first we need to find what the classical turning points are. Those being whenever the energy of the system is entirely equal to its potential at a point x naught, and then you solve for x naught and you have the classical turning point. Um, so that's going to be 2e over m omega squared under square root um, will be x naught. And so the left classical turning point will be minus x naught, and the right classical turning point will be positive x naught. So we can write our integral now as being minus x naught to x naught of the square root of 2m e minus m squared omega squared x squared over x. And I'm going to factor out a factor of 2me. So we're going to get, actually, on the outside, square root of 2me. And then on the integral, it's x naught to x naught. It's going to be 1 minus m omega squared x squared over 2. Right? Yeah. And 2e on the bottom, actually. Okay. So now we can do a u substitution. We can say that u is going to be equal to the square root of m omega squared over 2e times x, and so the differential will just be that same constant m omega squared over 2e times dx, and you can solve for dx to change over your differentials. And also, if you plug x naught into this, you just get 1, because this is 1 over x naught pretty much. You get minus 1 and 1 for the bounds of your new system. So now we're looking like this integral is going to be, I'm going to box this off a little bit. The integral is root 2me times the square root of 2e over m omega squared. And now it's the integral from minus 1 to 1 of 1 minus u squared du. And I think I've done this integral once before on this channel somewhere. But this simplifies to 2e over omega. And then that integral typically just gives you pi halves. So pi halves. And then we're going to set that equal to the pi h bar and plus a half stuff. We're going to simplify a bit. The pi's will cancel out, these 2's will cancel out, and so you'll find that En is equal to h bar omega n plus 1 half. So you find that the WKB approximation for the energy eigenvalues for the harmonic oscillator are the exact energy eigenvalues for the harmonic oscillator. So it's a pretty darn good approximation then. All right.